So we are on to chapter 3. We're now in section 3.2. So we are now going to be talking about the norm, the dot product, and distance in real space. So I realized I accidentally made a typo on the syllabus. So we are just going to be going over sections 3.1, 3.2, and 3.3. So we will not be doing section 3.4. So take note of that. So when you're thinking about your exam, these are the 3 sections that you're going to want to know. So like I said, we're going to be learning about the norm, the dot product, and distance in real space. So here is going to be the notation for the norm of V. So it's written like this. You've got V here, and it's got its 2 little parallel lines on either side. So that is the notation. But the norm of V is also, if you think about it, it's the length of V or the magnitude of V. I'm sure you guys have run into this before. So when you think norm, you're going to think length. You're going to think magnitude of that vector V. And we're going to have a teeny tiny refresher on the Pythagorean theorem. So this is definitely something that is very, very old. It's a really, really important concept in Euclidean geometry. We have these 3 sides of a right triangle, don't forget. So basically, this theorem we can be written as an equation relating the lengths of side A and B and the hypotenuse C. So here you see this little triangle here outlined in black. But the side, it's a right triangle here. So the sides A, B, and C, how those can all be related. And hopefully you remember your Pythagorean equation, where C squared equals A squared plus B squared. And so C is going to be the length of your hypotenuse, which I'm sure that you guys are all very familiar with. But I don't know, maybe you guys didn't know this, or maybe you might want to have a refresher. There's a lot of debate about the history of this theorem. But it is named for the Greek thinker Pythagoras, and Pythagoras was born around 570 BC. So they've been talking about this stuff for a long time. So we are going to be making use of this relationship where A squared plus B squared equals C squared, and C is going to be the length of the hypotenuse along that longest edge. So we are going to be using that to calculate the norms of our vector. So if we look at here, we have this vector V. It's described by its components V1 and V2. So who can guess then what the norm of V is going to equal? We make use of that Pythagoras theorem. So what do we think our lovely norm of our vector V is going to be? If we think about this length of our vector V here, the norm of V, we kind of liken this to the hypotenuse of a right angled triangle, wouldn't we? So we'd be able to make use of that relationship from Pythagoras. So you're on the right track here with some of you saying, let's see, we've got V1 squared plus V2 squared. But we have to remember that if we're actually solving for V, what's one other extra thing that we have to make sure that we do? Because we can't forget. Don't forget, you have to take the square root of the whole thing to actually get the answer. So here would be V1 squared plus V2 squared. So to actually get this length of the hypotenuse here, you'd have V squared would equal V1 squared plus V2 squared, but then to actually get that length V, you'd have to take the square root. So don't forget that. All right, well, that's obviously kind of easy in 2 space, right? So now we got to actually think about it in 3 space. What are we doing? So here we're trying to, I'm gonna go ahead and zoom in on this a little bit here. So here we've got that same vector V that we're trying to determine the norm for. Now, don't forget, that is the length or magnitude of this vector V, and we have this notation. So now we have a couple things that now we're going to need to be taking multiple terms into account, because now, if you notice, now we're dealing in 3 dimensions. So now we're actually going to be looking at the sum of this vector along this line here, and then we do a third one to have our 3 space, and here we end up at the terminal point P. So with those, if we start to apply Pythagoras' theorem here, we'd have what? We'd have v squared, the norm of v squared, that would equal our OQ squared. So that's this one here, OQ squared, plus our QR squared, plus our RP squared. So here's this other RP right here. So we'd have our vector and its three components. And so in this case, for three-dimensional space, we'd be using Pythagorean's theorem. But now our norm of V is going to be the square root of all this jazz now. So now it's of three different components. So V1 squared plus V2 squared plus V3 squared. Since we are now in the three dimensions, we now have three components to that terminal point. So it's kind of an interesting thing. We're making use of this particular Pythagorean theorem twice here. So it's cool stuff. Here is going to be your definition 1. So if you have a vector in real space, it depends on the problem, you know, what dimension we're going to go up to. So all the way through Vn, then the norm of V, so don't forget, it's also the length of V or the magnitude of V. It's denoted by this notation. So we looked at this. It's going to be defined by the formula, and we've just done that, where it's going to be the square root of the sum of the squares of all those components. So we are going to be able to calculate our norm of a vector into many, many dimensions. So we will go ahead and give it a try. But just wanted you to make sure that you realize with a lot of these definitions, you're going to want to look for, okay, what dimension of real space are we looking at? You know, for these equations, are we going all the way through to that nth dimension? Not all definitions are going to apply to all dimensions, so you do want to be careful about reading these definitions. But in any case, we'll go ahead and look at our example 1. So if we had a vector v that was in 3 dimensions, so we got R3, how in the world would we go ahead and calculate then our norm of v? So what would that equal? Yep. So if you're following Amaya's directions there, where you're taking the roots of all your different components squared and summing them up, what would this equation be? So somebody's got the root of 15. Do we agree? Or, oh, looks like they changed that to the root of 14. Yeah, so we'd be doing the square roots of -3 squared plus our second component here, 2 squared, and then plus 1 squared. So hopefully if you did all those, you'd end up with the square root of 14. And so don't forget this value. Now keep in mind, what are we solving for? We're solving for the norm of V here with this. So keep in mind that this is going to be the length and magnitude of V. All right, so let's try this next one. This one's in 4 dimensions. So now we got 4 components to work with. So here, our norm of V is going to equal the square roots of all kinds of jazz here. We've got 2 squared plus our -1 squared plus our 3 squared plus our -5 squared. And then if you did all that math, hopefully you could end up with the square root of 39. Now, keep in mind, we are solving for the norms, not to be confused with the vector itself, but this is going to be the length or magnitude of that vector. So, because we are solving for the length or magnitude, so here you're going to keep in mind your theorem 3.2.1 here. If V is a vector in real space and if K is any scalar, then that norm of V is going to be greater than or equal to 0. And that makes sense because when we're thinking about the length or the magnitude of that vector, we're not really taking into account direction, right? We're just looking at the length and the magnitude. So that is going to be equal to or greater than 0. And then that norm is going to equal 0 if and only if we're talking about if the vector is the 0 vector there. And then certainly we have this scalar k. So then the norm of kv is going to equal the absolute value of that scalar k multiplied by the norm of v. So basically multiplying a vector by a scalar multiplies its length by the absolute value of that scalar. So keep that in mind. So then we have this next concept where we're talking about unit vectors. So this is something that you're going to want to keep in mind. So here we have a vector of norm 1 is called the unit vector. So we know that the square root of all those different sides squared is going to be equal to 1. So what they have given us is that we have a definition here for the unit vector, and they're calling this, in this case, the unit vector u. So handy dandy there, they're calling it u for unit vector. But you're going to be able to solve for this unit vector because we have a nice little equation here where we're going to be multiplying v by the reciprocal of its length or its magnitude here. And so by solving for u, this unit vector is going to be in the same direction as that vector v. So if we ever need to calculate the unit vector, we're going to be able to do so with this equation. So here we'll go ahead and take a look at that. So here, if we look at example 2, here it says find the unit vector u that has the same direction as v. Ooh, okay, so we've got our little equation for our unit vector. Here we've got u equals our reciprocal of a norm times the vector v. And we know that we have our vector v up here at 2, 2, -1. So what do we want to do? Well, chances are one of the easiest things to do would be to go ahead and calculate that norm of v. So here we've got our norm of v that we're going to go ahead and calculate. And that's going to equal, since we just did all this stuff, that's going to be 2 squared plus 2 squared plus -1 squared. So who can tell me what all that equals? What is going to be, yep, looks like Christopher's got it. Yes, all of that. We'd end up with the square root of 9. And then all that obviously is going to reduce to 3. So now as our next step in solving for that unit vector, here we now have 1/3 times our vector v. And so now we can go ahead and say u is equal to 1/3. And then we know our components of v up here. So 2, 2, -1. And then that's going to give us 2/3, 2/3, and -1/3. So that is what our unit vector is going to end up being. And just so you know, you're going to want to do it for yourself, but don't forget that the norm of a unit vector equals 1. So you can kind of go through and prove that to you. But if we were to go ahead and find the norm here of u, that would end up equaling 1. So here we have solved for a unit vector u that has the same direction as v. Now, this is for this unit vector u. It's the same direction as v, and so v here could be particularly anything, and you could find that unit vector for it. However, just so you realize, there are some standard unit vectors. So they're called standard for a reason. So just keep in mind, we do have some standard unit vectors. So if we're looking at the 2 dimensions here, so here on the left, we're looking in 2 dimensions. So the standard unit vector for the x-axis, it's going to be described by the components 1, 0. So it is the standard unit vector along the x-axis here. So another way that if you're only dealing in 2 dimensions, a lot of times they're going to use the letters I and J to describe the standard unit vectors for the x and y axis. So here for I, that's going to be the standard unit vector in the x direction. Here we have it for the y direction. So this component's going to be 0, 1, where now you have the 1 in the y component position, and it's going to be represented by j. Then if you have 3 dimensions, they use I, j, and k. So you'll notice then with this third direction along the z-axis, now the components for that standard unit vector is 0, 0, 1. So these are going to be your standard unit vectors. Now, you might ask yourself, what to do if we have many more dimensions? What if we're not dealing in just the x, y, and z axes? What if we've got more than 3 dimensions? So in that case, most likely you're going to be seeing the notation is going to be, they're going to use the small letter e. So just realize there's going to be quite a few ways that you're going to have to remember that these things are notated. So here, every vector in real space can now be expressed as a linear combination of standard unit vectors. So here you're going to want to make sure that you go ahead and you look at this. So you're going to want to check out your standard unit vectors. You're going to want to check out how you're writing them. If you're looking at more than 3 dimensions, you're going to be using the little e. And so now I definitely want to make sure that we look at example number 3. So we're going to check this out. So keep in mind, they have a tendency to use I and j if you are talking about 2 dimensions. They use I, j, and k if you have the 3 dimensions. Once you get to more than that, then you're going to have e, and it's going to have different subscripts for however many dimensions you have. And then, like I said, you're going to want to keep in mind that every vector can be expressed as a linear combination of standard unit vectors. Okay, so here we have, for example 3, how would we write this particular vector as a linear combination of the standard unit vectors? Well, I'll go ahead and show you. You've probably already looked at example 3. But don't forget, so this one we're looking at 3 dimensions here. So we're going to have our notations using the I, j, and k. So here we would write this as 2i minus 3j plus 4k. So here this vector would be a linear combination of these standard unit vectors. Now, the other thing I should mention with these standard unit vectors, one thing I forgot to mention, as you will notice, their origin here is going to be at 0. And hence they're going to be, that's part of their definition as being standard. They're going to have those initial points at 0. Now, as we saw in example 2, you could find unit vectors for other different positions. So this here is not a standard unit vector. These are, because they have their origins here at 0. Okay, so then here with the next example, in example 3, we're looking at 4 dimensions. So they've decided to go ahead and use lowercase e for this one. So here, in order to write this as a linear combination of the standard unit vectors, here you would write it as 7e1 plus 3e2 minus 4e3 plus 5e4. So here you'll notice they're using a lowercase e, and then now they're just doing, subscripts of e. So e1, e2, e3, e4. All right. So we have talked about the fact that we had calculated our norms of our vector. But the other thing that we might also want to think about is kind of figuring out the distance between 2 points. So we're going to want to think about this in terms of distance between 2 points instead of necessarily finding the norm of a vector. So here we have this P2. It's going to have the components x2 and y2. Here are P1. Its components are going to be x1 and y1. So here, if we wanted to think about this as calculating the distance between 2 points, we'd be actually calculating the distance d. But in a similar way, we'd want to think about then finding the distance between P1 and P2. And we want to find that distance, and so it's going to be very, very similar to what we did before with the norm, but now we're finding the distance between those points. So here our equation is now going to be, here we're going to do a similar thing with taking advantage of what we've done before, except now to determine the distance between these 2 points, now we're going to take that difference between x2 and x1. So here we're going to say x2 minus x1, and then we're going to square that amount, and then plus the difference between our y2 and our y1 components. And then that's going to be squared. And then we take the square root of all that, and that is going to give us the distance between 2 points. So before we were calculating the norm of a vector, here we're thinking about it in terms of calculating the distance between 2 points. In this case, it was in only 2 dimensions, so not too rough there. But as you can guess, of course, we can do this for higher dimensions. So once again, we're going to be trying to find the distance between these 2 points. So now if we think about, okay, now this is going to be in 3 dimensions. So now P can be described by x2, y2, now we've got a z2. And then our P1, its components, we've got x1, x2, sorry. Scratch that, I'm thinking in terms of x. Got x1, y1, and we've got z1. So now if we wanted to find that distance between all of them, here we're going to be looking at distance from P1 to P2. And now this is going to be the square root of all these terms. So now we're going to take x2 minus x1. And that's going to be squared, plus, now we take y2 minus our y1. Square that, plus our z2 minus our z1 squared. And then you take the square root of all that, and you're going to get the distance from P1 to P2. Now, you do need to make sure that you do take note of the direction, because then you're going to know which one you need to subtract from which. So here we had this, we considered P2 our terminal point, so then we subtracted x2 minus x1, we did y2 minus y1, and we did z2 minus z1. So here we have found the distance between P1 and P2. All right, so got that. Now, here, if you want to have it in terms of a definition, we've got our definition 2 going on here. And this is, here we've got, if U and V are points in real space, then we denote the distance between U and V by duv and define it to be. And then here they've gone ahead and they've done exactly what we've gone ahead and done in the previous example. So here they're taking the difference between those components, squaring those differences, then they're taking the square root of all those terms, and that is going to be the difference here between the vectors U and V. So you're going to be able to do this many, many times. So here we'll go ahead and look at example 4. So we'll go ahead now and use it with some real numbers. So if we look at here, we're going to want to calculate our distance. We're going to use our proper notation now. And distance between U and V. Go ahead and write it like this. And so now, I'm going to take the square root. We're now working in the 4th dimension. All right, so now we're going to have 4 terms under here. So now we're going to have 1 minus 0 squared plus, we've got now 3 minus 7 squared. Now we've got negative 2 minus 2 squared. And then we've got one more, we've got plus 7 minus 2 squared. Woo. So now we're calculating the distance between these 2 vectors. And now hopefully if you have done your math correctly, you should get the square root of 58. And so you'll notice that we're going to kind of be easy on ourselves. A lot of the answers on the test, you can go ahead and leave it in square root form like this. If I need you to actually calculate the decimal, I will make sure to tell you. If you do get an exam question where I do ask you to actually solve for this square root, you're going to want to make sure that you pay attention to how many decimal places I tell you to take it to, because you wouldn't want it to get your answer unnecessarily incorrect. So just wanted to show you that. So we've kind of looked at, okay, what is the length or the magnitude of a vector, its norm? And then we've thought about also what are our standard unit vectors. We also know how to calculate a unit vector. Keep in mind, a unit vector does not necessarily have to start at the origin. That is left for our standard unit vectors. Then we want to make sure that we also know that we can express any vector as a linear combination of unit vectors. That's going to be important. And then now we know how to do the distance between 2 points, or you can think about it as the distance between 2 vectors. And so now what we're going to be looking at is going to be the dot products now. Yeah.
So like what we just went over, is that the same thing as the norm, or is that different?
Yeah, you want to think about these as being the distance u between 2 separate vectors. So here we're going to be calculating distance, or you could think about the distance between 2 points. But when you're thinking about the norm, you're specifically thinking about what is the length or magnitude of that particular vector. So it's a slightly different concept there.
So when we find the distance between 2 vectors, we're basically doing the distance from the point of...
Yeah, if you had subtracted one vector from another.
Oh, okay.
So here, yeah, so here this was just the length and magnitude of this vector, the norm. Let's see. Whoop. Here, once again, we are calculating norms just based on the components of that vector. And then now, let me get to that. Now we're thinking about, okay, now we're thinking about distances. Here's a distance between 2 points. So here you'd have to actually, if you're thinking about this as a point and that as a point, now you're going to be subtracting x2 minus x1, y2 minus y1. And then here we're also thinking about what is going to be the distance between 2 vectors. So here we're actually subtracting the components of each of those vectors. So see how this is 2 different vectors on this one?
Yeah, and so the direction doesn't matter?
I'm sorry?
The direction doesn't matter?
No, because if you think about, if you're just thinking about distance, you know, that is going to be kind of like an absolute value, so to speak.
All right, yeah, I see what you're talking about. Thank you.
Yeah. So now, no, those are good questions. So now we are going to be looking at the dot product. Oh boy. So before we're looking at, okay, we know how to add and subtract vectors. We know how to calculate their norms. We can find the distance between 2 points. We can find the distance between 2 vectors. Now we're actually wanting to do some multiplication on our vectors. So now we want to have some useful ways to manipulate vectors in other ways. So one of them is going to be the dot product. So here we're going to have, when they're initially describing this, they want you to realize that this is going to be in 2 dimensions or 3 dimensions here. So here they've got, let u and v be non-zero vectors in R2 or R3. And here they're positioned so that their initial points coincide. So you'll notice that in each of these little figures here. And so here we also want to recognize what is the angle between u and v. And we want to make sure to be able to do this dot product that it needs to go ahead and satisfy the inequality that the angle between u and v, this angle is going to be between, so it's going to be greater than or equal to 0 and less than or equal to pi. So let's kind of look at this and we'll check out, okay, what are these angles between u and v? So here's angle theta here. Now, would you say that it satisfies the inequalities of that angle being greater than or equal to 0 or less than or equal to pi? How many of you, what would you guys think? Do you think that inequality is satisfied by that angle theta I've drawn there in that first figure on the left? So yeah, it looks like, yeah, you guys are saying yes. Okay, yeah, that angle falls somewhere between 0 and pi. All right, let's look at this angle here, angle theta here. What do you think? Does that satisfy our inequality? Looks like yes, some of you are saying yes, so yes it does. So this angle is between 0 and pi as well. Ooh, what do you guys think about this angle theta? Ooh. Are we still within that inequality? Looks like some of you are saying yes as well. So I'm testing to see whether you guys remember this or not. All right, let's look at this one. Ooh. What if I said this angle here? Does that satisfy the inequality? Oh, we got a lot of no's on that one. Yeah, so no. No on this one. All right, well, let me I'll call this theta 1 here. What if I asked you about this one, this theta 2 here? What would you say for that one? Ah, interesting. Yeah, Mahmoud and Brendan say yes. So this one, yes, would satisfy the inequality. So just as a little refresher here, if you don't remember what some of your angles are in radians and degrees. So just think about it this way. So we've got to have, to satisfy our inequality, we've got to have our angle be in this range here for theta. So just realize here from 0 to 180 degrees, all of that is going to be pi radians. So this might be a little refresher of how these work. This one here would be pi halves radians here at the 90 degrees point. Here, obviously, here it would be 0 radians if this was our starting point. So here, anything over 180 degrees, that's going to be more than pi radians, right? So it's not going to satisfy that inequality. So you would have to, like I said, this one, if you're looking at it from this smaller angle, this would satisfy the inequality. If you're taking this larger angle around the outside here, that would not solve the inequality. So just a little bit here. If you do go all the way 360, that's going to be 2 pi radians. So if you went all the way around the circle. So just a little refresher there in case you didn't remember how many degrees you were going in terms of pi radians or not. Okay, so we've got now, give me a second, my computer has frozen a little bit. So now you ask yourself, what are we going to use all that for? Oh my goodness. So now we're going to be doing the dot product. So keep in mind, this is showing you in terms of if you have vectors u and v, that they are non-zero. And we're looking at right now in 2 or 3 dimensions, so R2 or R3. And if theta is the angle between them, between u and v, then the dot product of u and v is going to be denoted by u dot v. So here you're going to want to pay attention to this little notation here. So you got a little dot there going on. So hence dot product. But anyway, that dot product of your 2 vectors is going to be the norm of u times the norm of v times cosine theta. And so if either u or v are equal to 0, then that dot product is also going to be 0. So I think that that's kind of probably obvious to most. So one last slide that we'll look at here is this is not in the book, but I've added a couple extra slides for reference. So you might want to go ahead and peg some of these. So like this is extra, so you might want to remember, you know, how many degrees is equal to how many pi radians. The other one you might want to bookmark is this one, the dot product. You might want to know what the cosine of theta is. for several different values. So I've gone ahead and I've put in this handy dandy little chart. So hint, hint. So the cosine of 0 degrees is going to be 1. You got your cosine of 30 degrees, 45, 60, and 90. So I would go ahead and bookmark this particular slide in case you need it. So then I have another little reference slide to remind you of some things in geometry in case you'd forgotten some of them. That's just in there if it's helpful. We're going to try not to rely on needing a lot of excessive geometry knowledge because this is kind of a standalone course. You're not supposed to have any prereqs. So these are just put in here as little refreshers. You shouldn't need a whole lot of geometry. But in any case, put that in there. So what you're going to want to be able to do with this is that here we're going to be using the dot product as well as the norms of our different vectors. And we're going to actually be able to calculate that angle between them by taking the inverse cosine. So you're going to want to take note of this equation as well, because not only is it informative to be able to kind of multiply vectors, but a lot of times it's very nice to be able to determine what is the angle between them. Slides here from your book about some things to remember about sines and cosines and angles. Here, you know, if you have an acute angle, here that's going to be less than 90 degrees. Obtuse angle, we've got more than 90 degrees here. You're going to want to keep notes of the dot products. This was also another little handy slide here to kind of remember. So you want to think about, okay, if the angle between two vectors is acute, then that means the dot product of those two vectors, it's going to be greater than 0. If you've got an obtuse angle between those two vectors, then the dot product is going to be less than 0. And then here's a really key concept here that if you have a right angle, then the dot product between two vectors is going to equal 0. So part of the interest in this is that, you know, here we want to explore a lot about what we talked about in the previous part of this chapter. We talked about, okay, we want to find the norm of a vector. Does anybody remember what the norm of a vector is? Yes, it's the magnitude or the length. So you might very well want to describe a vector according to its norm. Then we want to have the ability to have some multiplication properties that we can apply. So we learned about the dot product. Does anybody remember 2 different ways that we learned how to do the dot product? Yeah.
x1 times x2 plus y1 times y2.
Yeah, so what was that called? You're kind of taking the dot product of what?
All the components.
Yes, good job. Okay, so does anybody remember another way that we did it? I'll give you, it involves an angle. I'll give you a little hint. So if we have a vector u and a vector v, I'll give you even a second hint. In the definition, this had applied to vectors in 2D and 3D, so R2 and R3. Does anybody remember what you do? Maybe I'll find that slide. This should give you another hint right here.
The inverse of the cosine.
So here it is. Here, this definition 3, you're going to want to check this out. So if you have non-zero vectors u and v in R2 or R3, and you have this angle between them, then the dot product, we also call this Euclidean inner product, of u and v is going to be defined as, here we go, it's going to be the norm of u times the norm of v times the cosine of the angle between them. So this is another way you can take the dot product for 2D and 3D vectors that are non-zero. Okay, so let's move on down here. We also looked at the component form, like you said. So here, if you have the dot product between u and v, this is here where we are now expanding this to, though, include more than just the 2 and 3D space. Here we've got vectors in real space all the way up to the nth dimension here. So here now you're going to do this in terms of the components of your vectors u and v. So here you're going to multiply the first components of u and v together, then the second components all the way through the n components, and then you're going to add up all those. So that one's a real simple one. Probably, I would say most people are probably going to use this method. So, all right, then. So here's the other thing that you want to make sure that you check out. You want to check out theorem 3.2.2. This is going to have a lot of algebraic properties of the dot product. So you have your symmetric properties, you got distributive property, you got the homogeneity property, positivity property. So check both of these out. Then you have your theorem 3.2.3. You obviously want to know what to do when you have the zero vector thrown in there and scalars thrown in there, what it is that you can and can't do. So make sure you bookmark that table. All right, so here's the other thing where we kind of left off last time. We were kind of talking about different angles. And so you'll have these vectors, and you'll certainly be able to find the norm of them. But the other thing that people are going to be really, really interested in knowing is what is going to be the depth, what's going to be the angle theta between these two vectors. And so keep in mind that this is going to apply to angles in real space to many, many dimensions here. So R to N. So here they've gone ahead and they've taken that dot product equation and then they've gone ahead and solved it in terms of theta. So here you're using the inverse cosine. And so you'll recognize this from the dot product equation. And so just realize that when you calculate this dot product, you're not going to be able to find theta unless this term here satisfies this inequality. So this term here for your dot product in U and V divided by the norm of U times the norm of V, this quantity here has to satisfy this inequality where it's got to be greater than or equal to -1 or less than or equal to 1. So keep this in mind. So that's going to be useful for you to not only know how to add, subtract, multiply all these different vectors, you're going to want to find their norms, you're going to want to find the angle between them because who knows what kind of application you might be doing. So here, just kind of this is basically a little bit more about that theorem that we just showed. And then we have some other different things that we're talking about in terms of two fundamental theorems. So we've got the triangle inequality for vectors, and I think that these are pretty intuitive. So here, if we just go ahead and zoom in on this. So I think that we kind of know this already, but if you think about it, the sum of the lengths of two sides of a triangle, so here we got the sum of U and V here, is at least as large as the third. So I think that that kind of makes sense. So U and the sum of U and V is going to be at least as large as this third side U plus V. So I think that pretty much makes sense. And so when you're describing it in terms of the norms, you would have this inequality like this. So the sum of U, the norm of the sum of U plus V is going to be less than or equal to the norm of U plus the norm of V. And then they're also looking at this when we're talking about the shortest distance between 2 points. So I think we can see that that easily translates there. So we'll have this same triangle inequality for distances. So keep in mind in this first one, we're talking about when we've actually specified that these are vectors. And so here we're looking at the norms, right? Because we're just looking at the magnitude or length. We're not particularly reporting this in terms of direction. And then this is going to be the inequality for distances between points. So go ahead and look at that. So here it is nicely written up for you in theorem 3.2.5. So you kind of want to check that out. And then here is this other theorem here that we have, 3.2.6. This is the parallelogram equation for vectors. And so all this is simply saying is, and I'll go ahead and get my highlighter here. What it's saying is that the sum of the squares of the diagonals, so here I'll go ahead and highlight these diagonals. So the sum of the squares of the diagonals is going to be equal to the sum of the squares of the four sides. So basically, the sum of the squares of what's in yellow is going to be equal to if we took the sum of the squares of all four of these sides. That's just basically what this theorem is telling us. So you are going to want to make sure that you take note of that equation there. Yes?
Does that equal to perimeter or the area of the parallelogram?
No, this is going to be the sum of the squares of the diagonals. So it won't be the perimeter. So the sum of the squares of the diagonal is going to be equal to the sum of the squares of the four sides. So that's going to be quite a bit more than the perimeter, right? It's going to be the sum of the squares of the four sides. Yeah. So that's what that theorem's about there. Yeah, so I've written it down here for you. So this is going to be the four sides. So basically, the sum of the squares of these two diagonals in yellow. So if I were to square both of those and add them together, right, that is going to be equal to what I would get if I took the squares of the four sides and then added those up. So it's just letting you know that those things are going to be equal. And that is going to be your parallelogram equation for vectors. And then we have one more. So here we have yet another way of reporting on the dot product. Now, what do you notice is different about this dot product? That's different from maybe how we've done it before. Yeah, we got fractions in there. No, this one in particular is making a relationship between the dot product. Oops, go back to here. The main takeaway here is we are relating the dot product to the norms. So here, this is going to be kind of a fundamental relationship here. So I'm not expecting you to do a whole lot with this, just to recognize this is yet another way that you can calculate the dot product for vectors in real space. Here, you're basically relating the dot product and making use of the norms of these vectors. So before we were looking at the components, and the other one, we had like an angle between them. This one's purely just relating the dot product to the norms of those. So then I feel like they did a lot at the end of this section and just kind of threw a lot at you. But basically, now they want to relate it back to all the different matrix multiplication that you have done before. So they're basically going through dot products as matrix multiplication. So what I would do is I would go ahead and bookmark this table 1. So I don't expect you to memorize this. Obviously, you're going to want to use your book for this. But they're showing you how to do the dot product in various forms. So this first one here, you have U as a column matrix and V as a column matrix. Well, in order to be able to multiply those, they have basically taken the transpose so that both of them are not column matrices. So you kind of want to see what they've done here through the manipulations here. So here, if you have U as a row matrix and V as a column matrix, then how you would do that. Here, if U is a column matrix and V is a row matrix, so the other way. And then we have, if they are both row matrices, what are you going to do? So I would just take a look at these. So like the top, they're both column matrices. At the bottom, they're both row. In the middle, they're showing you what would happen if one was a row, one was a column, and vice versa. So just kind of take notes of that last table there. Not too hard. But basically from all these different matrix multiplication things that they've led you through, one thing I will lead you to is they have some resulting formulas that you are going to want to take note of and bookmark. So as a result, let me get down here. Ooh, we got our... So here's your table. And so you will have a resulting formula if you do want to take the dot product and you are going to involve matrices. So here, take a look at formulas 26 and 27. Here will be a way for you to go ahead and calculate these. And you'll be able to see from table 1 how they arrived at those. So if you had a matrix multiplied by this vector U, and then you wanted to take the dot product with another vector V, here is how you would calculate that. And then same difference if you had this matrix multiplied by a vector V, and then you're going to take that as a dot product with vector U, how would you go ahead and calculate? So here you have, so A is going to be this matrix. Here you've got U, here you've got a column vector, V is another column vector. So AU, here you've gone ahead and multiplied A times your column vector U, and you're going to end up with this resulting column matrix. And so then they've taken AT, the transpose of A here times V. So they've gone through and then they have achieved this vector. And then now, so here we've gone ahead from these calculations here. We've calculated AU, and then we've also calculated the transpose of A times V. And so then they have gone ahead, and then they've gone ahead and done their dot product, where here you can actually do this by the components then.